Good morning, good afternoon, or good evening to whenever you are watching this. My name is Aaron Harvey. I am currently studying towards a BSc Honours in Genetics at the University of Pretoria. I've been a tutor at Teneo for more than a year now. My specialities include physics, life science, and mathematics, ranging from grade 7 to matric. I have tutored it all, and I know it all by now. Today, I thought I would give you a demo lesson or demo tutor session, I should say, in physics. Now, I know when it comes to physics, a lot of students struggle with the concepts of momentum and how to tackle some of these questions. So today, I'm going to try and pack a quick, hopefully informative, hopefully helpful video discussing some of those concepts and also addressing how we could attack some of those questions. Let me go and share my screen with you. So let's get started. Well, before I get started, I just need to address that some of these summary notes have come from Mindset Learn Online, which is a very helpful tool for all students, which I highly encourage everyone to look. It's free to access and has a plethora of notes that are very useful and helpful for studying, but also helpful for me in hopefully sharing with you some of the concepts that they summarize. So let's get started. Momentum. What is momentum? Momentum can be defined as the product of an object's mass and velocity. So basically put, you're going to take how fast the object is going, velocity, and times by the mass of the object. So this can be written very simply in the equation as seen here. P equals mv, where P is our momentum, m is our mass, and v is our volume. Now, with this equation, you have to make sure that all your variables are in a specific unit. You need to ensure that your mass is in kilograms. So if in a question they were to say this object weighs 600 grams and is going at 1 meters per second, you have to realize that if you want to calculate the momentum of this object, you'll need to convert that 600 grams into 0.6 kgs, as this whole formula is based on kgs in terms of mass and also meters per second in terms of velocity. But most times in questions, velocity is very straightforward. The only time they might trip you up is if they were to give you the velocity in, say, centimeters per second or in kilometers per second. But most of the time, they will keep it at meters per second. And the only place they'll try and trip you up is by giving you the grams of an object rather than the kg. And now when we look at this formula, we also need to realize that momentum has a unit. And its unit will be simply kgs per meters per second. And how did we come up with that unit? Well, momentum is the product of an object's mass and velocity. So it's mass, kgs, times meters per second. So just remember that your momentum, its unit will be kg meter per second. So with this whole concept in mind, we can then start moving forward. And we can think about when objects experience a change in momentum. So momentum remains constant in a system unless it's acted upon by a third force. Well, not a third force, a third party force. Something comes and interrupts its isolation. So what does it say here? If the object changes direction, when changing velocity, it will experience much greater change in momentum. Okay. This touches on another very important topic that isn't specific to just momentum, but is specific to any vector value that you're working with. Direction, direction, direction. When it comes to physics, your plus and minus signs are extremely important. It is the difference between getting a velocity of 20 meters per second and negative 20 meters per second. Now, even though your value might be correct, if your sign is incorrect, your answer is unfortunately incorrect. So specifically within momentum, we'll see that it does become very important when we're looking at our signs. But it's just a general tip for all of physics. Be very, very cautious with your signs and always note direction. If you're working with a vector, you need to remember that vectors have magnitudes and direction. So what we were going on about here before I went off on my tangent is that if there is a change in momentum, so a change in momentum can only be done if there is a force applied. So if we look at this nice, pretty formula that's next, they'll say, in order for an object to change its velocity or change its direction, a net force needs to be applied to this object. And the net force can thus be calculated as the change in momentum, delta P, over our change in time, delta T. So what this is saying is that the force acted upon this object is equal to the change in momentum of the object over the time that this force is happening. Now, this is a very important formula, as this then can build on to our Newton's second law, which is F equals ma. Our force is equal to mass times acceleration. Because what it is saying is that acceleration will only occur if a force is being applied. But you should hopefully know your Newton's laws by now, Newton 1, 2, and 3. If not, I would highly suggest going and revising them, because now we're actually going to come in with an amendment to our Newton's second law, where it says that our Newton's second law in terms of momentum is that the net force acting on an object is equal to the rate of change of momentum. Now, if you happen to struggle with remembering definitions or the laws, sometimes your formulas can help you. You will most likely be given a formula sheet with whatever test or exam that you do. And don't overlook your formula sheet for definitions. Because if we look at this definition in for Newton's second law in terms of motion, in terms of momentum, the net force acting on an object is equal to the rate of change of momentum. Okay, so net force is our F net there. And it is equal to, equal sign, the rate of change of momentum. When we're talking about the rate of change of something, we're talking about how something changes over time. So we can actually see that this definition is just a word formula of this actual equation, that our F net, the force acting on an object, is equal to the change in momentum over time, or the rate of change of momentum. But as I said before, units are extremely important. So we need to look at our units. So our net force will be measured in newtons, which hopefully you will know by now. Our change in momentum, even though it's a change in momentum and not just purely a value for momentum, it is still measured in the same units, our kg meters per second. And our change in time, again, even though it's a change in time, it is still measured in the same unit as time. And in this case, it does need to be seconds. Because in a lot of questions that you will do, you will see that this change in time will be minuscule. It will be 0.000 something seconds. But you always need to remember that you will need to make sure your time is in seconds. Just like with the previous formula, I said that you need to ensure that it's in kgs, your mass. Because unfortunately, sometimes questions will trick you and say the change in time was in milliseconds or was in kiloseconds. And you need to be able to understand and remember that you actually need to convert that unit or that value into the correct unit. But now that we've covered a lot of the theory when it comes to momentum, we can start looking at collisions. So a collision is a very, very specific way that examiners and test makers like to ask momentum. Because if you look at any question that you are given in your test or an exam, you'll see that it most likely follows the law of conservation of momentum, which states that the total linear momentum of an isolated system will remain constant or is conserved. What this means is that in an isolated system where nothing is interfering, there's just the system. So there's no friction, there's no air resistance, there's no random person pushing an object. It is isolated. Whatever momentum is in that system will remain unchanged unless something acts on that system. So if you think about something in space and you are, say, throwing a tennis ball in space. After you've thrown the tennis ball, you've released the tennis ball. There's now no longer a force acting on that tennis ball, but it will be moving through space at a constant velocity, and it will have a constant mass. And when it's in space like that, if there's no like meteors hitting it or anything, its momentum will be conserved. So that tennis ball will have the exact same momentum from the minute it leaves from the second it leaves your hand to whenever something else interacts with it, because there will be no air resistance, no friction, no external forces. And this is a very nice way that examiners can ask momentum. So when you're in an isolated system and you are following the law of conservation of momentum, there again is a nice little formula that you can write out, which states that the sum of our momentum initially, so whatever happens before something happens, will be equal to the sum of the momentum final. Another way that this formula can be written is our change in momentum. Oh no, excuse me, I am taking one step ahead, is our momentum before must equal our momentum after. Now, this obviously isn't a very scientific or mathematical way to write this, but if you understand the concept, that is the main point of what I tried to teach. So we're saying that the momentum before is equal to the momentum after. If that is not making sense, we will get to it in a minute when we actually address a question together. So this formula can actually be broken down even further. This momentum, the sum of momentum initial is equal to the sum of momentum final. Because if we remember from earlier, our momentum is equal to mass times volume. Why is that not writing? There we go. Mass times volume. So we can actually write this formula differently. We can say that the momentum before will be equal to the mass initial times velocity initial is equal to the mass final times the velocity final. Because this is just writing out our momentum P into its other variables. And now, obviously, in isolated systems, we're not going to always have a singular object. But because we talk about the system, that whole system's momentum will stay constant. So you could then end up with formulas looking similar to this one here, where you've got your mass times your initial velocity of object 1 plus your mass times your initial velocity of object 2 is equal to the mass times the final velocity of object 1 plus the mass times your final velocity of object 2. So the idea remains the same, as this whole first portion is your sum of momentum initial. And the second half represents your sum of momentum final. Or, as I would say, your momentum before is equal to your momentum after. And there are two types of collisions. There are elastic and inelastic collisions. And the main difference between these two is that in an inelastic, where is my pen? In an inelastic collision, the total kinetic energy, so total kinetic energy of the system is different to that afterwards. Now, let me just check if I've said that correctly. Oh, okay, I highlighted the wrong word and got myself a little confused. Unfortunately, that does happen in live tutoring, but at least I picked it up. There's the word I'm looking for, elastic. If our collision is elastic, that is when the total kinetic energy is, where's the word I'm looking for, is equal. There we go. The kinetic energy of the system before the collision is equal to the kinetic energy of the system after the collision. The collision is said to be elastic. Whereas, however, if they are not the same, the collision is said to be inelastic. Now, this is mostly theoretical. And one thing that I try to get across is that I can explain things to you and I can help you understand, but I unfortunately can't learn definitions for you. So I can help you maybe make some rhymes or some anagrams or ways to remember these things. But unfortunately, you are going to have to do a bulk of the learning for yourself. I'm here to facilitate extra understanding and to help you address questions. So don't feel scared to ask anything whatsoever at all at any point in time. But at the end of the day, I can't learn definitions for you. So try as hard as you can. If you can't, we can try together. But this is a two-way street. I will hope that what you learn from me and what you take afterwards, that you put it to use. Because there's no point in coming to these sessions to then just forget everything. These sessions are aimed at helping you, and you also need to put in a little bit of effort. But now that I'm done with my little diatribe, let's move on to our next section, which is impulse. Impulse is a branch of momentum, and impulse can be defined as the product of the net force acting on an object. There we go. Net force acting on an object and the contact time that that net force acts. So as we can see, there's a very nice formula over there. Impulse is equal to F net delta T. This is defined as a change in momentum. So if you go back to your definition page, you'll see that impulse can be defined as a change in momentum. And that change in momentum is due to our net force acting on our net force acting over a change in time. Now, I'm going to just scroll up to remind you of an equation we looked at earlier. We looked at this equation. And if you notice, it's actually got all the same components. So both of these formulas have the same variables, just written differently. So you'll see that your delta t, your change in time, is no longer on the right-hand side of your equation, but is rather on the left-hand side of your equation. So you can rearrange this back to the original formula, or you can use it like this. Because in this form, you are then talking about impulse. So if you are ever asked to calculate impulse you can calculate as the change in momentum, which is also equal to your net force over a change in time. But now, because this formula has been slightly rearranged, we need to go and look at our units again. So our change in momentum, because it is a change in momentum, it is still going to use the unit of momentum, which is kg meters per second. Our change in time is still going to use the same unit as time, which is seconds. And our net force is going to be measured in newtons. But when we're looking at impulse, Impulse is defined as the change in momentum, defined as the net force acting on an object and the contact time that that net force acts. So if you look at F net change in time, which is equal to impulse, you'll see that its unit can also be written as Newton seconds, because it is our Newton from F net times our second for change of time. So if you are asked to give a unit for impulse, it is your Newton seconds. But now, that is all the theory. Let's go and look at a past exam paper from 2017, because I believe that a lot of these concepts, it's great to understand them, but if you can't apply them, that is where a lot of the students struggle. So one of my goals in the tutor sessions is to help guide you at how to attack these types of questions, how to know what they're looking for. So let's jump in. An important thing to do is to first analyze your question. So you're going to read through it slowly and carefully. So they say a 2 kg block, 2 kgs is a very important thing to notice, is at rest. Again, at rest is a very important thing to notice, because what does at rest mean? It means that the object is stationary. It means that at that point in time, its velocity is 0. So a lot of times questioners won't tell you, oh, the velocity is 0. You have to be able to understand that if an object is at rest, it is sitting still, it is not moving, it has a velocity of 0. They also mention that it is on a smooth, frictionless, horizontal table. So smooth, frictionless. What this is telling us is that there's no external forces acting on this block. So we can sort of start to see that we're going to have to probably look at a conservation question. They also tell us that the length of the block is x. So kind of self-explanatory. We are probably going to have to figure out what x is, but we'll get to that step when we need to. They tell us that the bullet of mass 0.015 kgs is traveling east at 400 meters per second. Again, those are two very important numbers to notice. What you should also notice is that they've given you the mass in kgs, which is perfect. That's what you want. It means you don't have to convert anything. Because if we're working with momentum, remember that we need to work in kgs. It's also important to notice that they've commented that this bullet is traveling east. So they've given us a nice little diagram here. East, so it is traveling to the right. This bullet then strikes the block and passes through it with a constant acceleration. So it means that as it hits the block and goes through the block, its acceleration is the same throughout. It says refer to the diagram below and ignore any loss of mass that the bullet and the block. Okay, so what I prefer to do is I like to go and fill out all the information I possibly can from the paragraph above that they haven't added, obviously. So we can already see that they've added that it's a 2 kg block. But what they didn't add there is that it is at rest. So that block, its velocity is equal to 0. They also tell us that the bullet has a mass of 0.015 kgs. Let me just go add our units there, and traveling at 400 meters per second to the right. So now that we have all of our information on our diagram, we can now start addressing some of the questions. Question 1 says, state the principle of conservation of linear momentum in words. So this is just a straight out definition question. You're going to have to regurgitate it. And as I said earlier, I unfortunately can't learn things for you. But if we think back to what we were talking about earlier, the principle of conservation of linear momentum states that let's go and get it in these exact words. The total linear momentum of an isolated system remains constant or is conserved. So now this is obviously a definition I got from someone's summary. You will most likely have been given a set of definitions, or it will be in a textbook or on a slate of slides. Go and learn whatever your teacher gives you. But as long as you understand the principle behind it, that in an isolated system, when there's no external forces acting on the system, the momentum of that system will remain constant. If you understand that fundamental, even if you can't remember that definition word for word, you can just write how you understand it and hope that maybe your marker is slightly lenient. But that does not mean you get to be lazy and not learn your definitions. Definitions are the groundwork for all of physics and for chemistry. So go and learn your definitions, but make sure you also take the time to understand your definitions. You are not a parrot, so try and find the deeper meaning. Try and make that definition make sense to you, not just writing out the words. Then we move on to the next part of the question, and they give us more information. The block moves eastwards at 0.7 meters per second after the bullet has emerged from it. So what are they saying here? They're saying that after the bullet has hit the block and left the block is now moving at a velocity of 0.7 meters per second eastward. Again, notice how they're pining on that direction. So make sure that if it is going eastward, that means that that block is traveling in the same direction as the bullet. And that will have a large impact on how you answer your question. Because they then now want to know, calculate the magnitude of the velocity of the bullet immediately after it emerges from the block. So now I know a lot of students go, oh, wow, how am I even going to start this? Remember that people who set your tests and exams, they set your tests and exams out in a certain way so that they guide your thinking. So in the previous question, they asked you for the principles of conservation of linear momentum. So if they've asked you that in the previous question, you are most likely going to have to use that principle here. And what does that principle say in a formula? It is that our sum of momentum initial is equal to our sum of momentum final. So what this means is that the momentum of our system before the collision is the same as our momentum of the system after the collision. And we can actually just go back and rewrite the formula that I showed you earlier. But let's take time to understand what we are doing. So what are we going to classify as before the collision? We're going to, oh, they've even labeled it very nicely for us. Before the collision, we need to see that we have two objects in our system, the bullet and the block. We know that the bullet, I'm not going to rewrite it again, but is going at 400 meters per second eastwards and has a mass of 0.015 kgs. And that our block is traveling at 0 meters per second and has a mass of 2 kgs. So we can then say that our momentum before the collision is going to be the momentum of our bullet plus the momentum of our block before the collision. So it's going to be the mass of our bullet, 0.015 kgs, times the velocity of our bullet, 400 meters per second, plus the mass of our block, 2 kgs, times the velocity of our block, 0 kgs. Now you can go and do those calculations, but this is what the momentum will be of the system before the collision. Now, if we're looking at the momentum after the collision, so I'm just going to draw around here. We again look at our system. Our system consists of our bullet and our block, which means that if we're looking at the momentum of the system, it's going to be the momentum of our bullet plus the momentum of our block. So let's go put in what we know. Our momentum of our bullet is mass times volume, times velocity. Our mass is 0.015 kgs times the velocity of our bullet. Oh, but we don't know the velocity of our bullet. So we'll just leave it as velocity for now. We then need to add the momentum of our block. The mass is 2 kgs, and they tell us that the velocity is 0.7 meters per second. Now, because they told us that the bullet is moving east, and then the block moves east, both of our velocities are going to have the same sign. Whether they're both positive or negative, that is up to you as the person answering the question. Just remember that whatever direction you assign a sign to, so in this case, I've assigned east as positive. You need to stick with that throughout. You can't halfway through the question decide that, oh no, you want east to be negative for this value. No, because if you have assumed that east is positive, any negative value when it comes to a velocity will actually indicate that your object is going west. But we now have the formula to calculate our momentum before the collision and our momentum after the collision. So we can write this out as a nice long formula. 0.015 times 400 plus 2 times 0 is equal to 0.015 times the velocity of our bullet that we don't know, plus 2 times 0.7. And what you'll notice is that you only have one unknown, the velocity of your bullet. Now, I will leave this here because I hope that you are able to solve for velocity in this case. If you can't, that is obviously then something we would need to go through together. But through this, hopefully you see that if you understand what is going on, you can tackle any question that they throw at you. But now we'll move on to the last question of this video, 4.3. They say, if the bullet takes 0.002 seconds to travel through the block, calculate the length x of the block. Now, I know a lot of students will be like, whoa, what is happening here? How did we suddenly now get to this? How are we going to calculate this? How do we use momentum? Keep in mind that all of physics is an integrated system. So momentum, you can't do in isolation. You can't do alone. So when it comes to this type of question, you need to think, what else can I pull from other facets of physics to help me answer this question? And hopefully what you'll realize is that they mentioned that this bullet has a constant acceleration through the block. You are also trying to calculate the distance or the length. Oh, I misspelled length there, but I'm sure you know what I mean. The length of this block. So if we think about it, you've got acceleration. You need to calculate distance or length. You've got an initial velocity. You've got a final velocity. Hopefully this should be ringing the bell of our equations of motion. This is how integrated physics is even in the middle of a momentum question like this, they can expect you to use your equations of motion. Now, I'm not going to go into detail. As I said, I would only discuss momentum in this video, but you should be able to, with your equations of motion, use your final volume of your bullet, your initial volume of your bullet, the time it takes to go through the block to give you the acceleration of your bullet. And if you have your final velocity of your bullet and you have your initial velocity of your bullet and you have the acceleration of your bullet, you can then determine the distance that it traveled, because your equations of motion work for one plane of motion. And if you remember from the question, they said that it's explicitly only going horizontally. Now, I hope that that was helpful and that you've learned something and that you maybe get a better understanding of what is to be expected in a tutor session with either me or one of your other tutors. Remember that there are many different tutors who will tutor many different styles. So don't be offended if you don't prefer my style of tutoring and you'd rather go with someone else, or if you're not liking someone else and would like to come and try me. You need to find that person that can teach you the best. So go and find them. And I hope that you have learned something today. I hope that you are willing to learn more. I am here at Teneo Tutors if you need me. So have a wonderful day for the rest of it, and I hope to see you soon.